If you're building a confidence interval for a proportion, if you want to find the sample size that you need in order for your chosen margin of error to be established at a given level of confidence, you use this expression for the margin of error. So your confidence level determines your critical value, your z star. So this is our standard deviation for the proportion, and we set this equal to the margin of error you would like to establish. So something to think about, if you want to guarantee that margin of error, you should use a proportion of 0.5 in the formula for the standard deviation if you don't have a better guess, if you will, for the real population proportion. So, but let's think about instead how to find the sample size that you need to establish a margin of error at a particular level of confidence for a mean. So here's the formula for the margin of error for a mean. Means involve t-scores, and then you have the standard deviation created by the standard deviation from your sample divided by the square root of the sample size. But there's a problem using this formula in order to find your sample size, because the t-score that you need has a degree of freedom. That degree of freedom is n-1. That's one less than the sample size. We're trying to determine the sample size. We don't already know the sample size, so we don't have a degree of freedom that we can use in order to find our t-score. So without having already solved for n, I can't find my t-score. I need to rethink this. So instead of working with the sample standard deviation, what we do instead is we take our best guess at what we believe the population standard deviation might be. Then we can divide by the square root of the sample size, and working with the population standard deviation, then we can go back and work with z-scores. So again, in practice, this is the relationship we use. However, this is the relationship we're going to use if we want to solve for n in order to find the sample size that we need to guarantee a particular margin of error. So in this case, I'd like a margin of error of plus or minus 4 years for the true mean date of the pennies in our penny container, and I want to use the 95% confidence level. So the 95% level, that would correspond to a z-score of 1.96, and we know the population standard deviation in the penny container is 11.9 years for the dates on the pennies. So again, you would use your best guess for that population standard deviation there. So I want the margin of error of plus or minus 4 years. So I want that to equal my critical value, which we'll use the 1.96 for our z-score. And we'll multiply by the best guess for the population standard deviation and divide by the square root of n so that we can solve for that. Now, there's a plus and minus on both sides of the relationship, so I don't really need to work with that. I can ignore that when I'm doing my solving here. So essentially, the first thing I'm going to do is divide both sides by, if you will, the 1.96. So at this point, you can think about cross-multiplying. So you have the 4 times the square root of n, and that's going to equal the 1.96 times the 11.9. And then to isolate the radical, I will divide by 4 on both sides. So this is the expression here then that you want to square in order to establish the sample size that you need in order to get the margin of error that you want. So we'll put that in the calculator here. So we'll take the 1.96 times our best guess at the population standard deviation, which we actually know is 11.9. We'll divide by the margin of error of 4, and that's the expression that we need to square. So what's important to recognize here is I really don't want to round this to 34. To guarantee that margin of error, I need that very small amount that remains in that decimal there. So you should always round your sample size up in order to guarantee that particular margin of error. So this really needs to be rounded up to 35. So having said that, then we can rethink then the conditions. We can certainly take a random sample of size 35 from the penny container. Can independence be met with that sample size? And the answer is yes, because we could take 10 times 35, that would be 350. And we know the size of the population, the penny container, is 518 pennies. So 10 times, our sample size is less than 10% of the population. So 10 times our sample size is less than the size of the population. So we're in good shape. So next, can the normality condition be met with this sample size? So remember, the normality condition when we're working with means involves the central limit theorem. So our sample size is 35. That's considered a relatively large sample. That's greater than or equal to 30. So the central limit theorem can apply here. So what this means is that we can believe that the distribution of x bar, the distribution of the sample mean, is approximately normal in this case. That word approximately is really important. It's not exactly normal. It's approximately so. So one more example, it's exactly the same idea. So let's say we want a margin of error of plus or minus 2 years. So we want to be a little bit more accurate here, but the method we're using is only at 90% confidence. So again, just to practice the solving here. So now I want a margin of error of plus or minus 2 years. Again, using z-scores, my 90% confidence requires a z-score of 1.64. And I can use the same population standard deviation divided by the square root of the sample size. Again, in terms of the solving, I'm not going to worry about the plus and minus here. So we're going to do the same thing that we did before. We'll divide both sides by the 1.64 so that then we can cross multiply. So we're going to end up with a relationship that looks very similar to above. So I've got my critical value of 1.64 times the standard deviation of the population. I'll divide both sides of this relationship by 2. So in order to solve for the size of the sample then, that will get me my margin of error. I'm going to square this expression to get rid of the radical on n. So here we go. This time we'll take the 1.64. We'll multiply that by the 11.9 and divide by our smaller margin of error that we desire. So we'll square this. So this time, the 95.22 approximately, we need to round that up to 96. And frankly, the reason that I designed this example was I just wanted you to think then about the other conditions. Could we take a random sample of size 96 from the penny container? And the answer is sure we could. But the independence condition will fail here. In order to use this formula for the standard deviation of our sampling distribution, I have to believe that I'm sampling less than about 10% of the population. I approximately need independence. And the 10% rule won't apply here. If I take 10 times my sample size of 96, that's 960. And that is not less than or equal to the size of my population. There were 518 pennies in the container. So we can't meet the independence condition here. Now, would the normality condition be met with this sample size? Well, sure, the shape of the sampling distribution will be approximately normal. Again, this sample size, which is a relatively large sample, so again, the central limit theorem would apply. So what this means is the shape of the sampling distribution. So if I take, lots of random samples of this size, the distribution of the sample mean, its shape will be approximately normal. But that really doesn't help me here because I'm not in a situation, the sample size is too large. I'm not in a situation where independence applies here. So I can establish the sample size I need, but because independence fails, at least with the population that we're working with here, this isn't a procedure that we'll be able to follow through on.